Welcome. Today we're going to pull back the curtain on one of the most powerful and maybe most underrated tools in your search arsenal, the wildcard. You know, that little asterisk that seems to work like magic? But as we're about to see, it's not magic at all. It's some seriously clever computer science.
I mean, you've definitely done this 1,000 times, right? You type the beginning of a word, slap a star on the end, and hit enter. And instantly, you get a whole list of results that all start the same way. So how on earth does a search engine sift through billions, maybe trillions of words to find every single match and do it in like a fraction of a second?
Well, the secret lies in choosing the right tool for the job. See, behind every search bar is something called a data structure. It's just a specific way of organizing all that information. And picking the right one means you're constantly fighting this battle between speed, flexibility, and how much memory the whole thing eats up. So let's dive in and see how engineers solve this puzzle.
Okay, so to really get the challenge here, we first need to understand the search engine's dictionary. And no, this is not the dictionary you have on your bookshelf. This is the master list of every unique word the engine has ever seen.
Think of it like a massive global address book. For every single term out there like cat or algorithm, this dictionary stores a pointer to every single document where that term appears. And the number one non-negotiable rule for this dictionary? It has to be unbelievably, ridiculously fast. So, if speed is everything, what's the fastest tool in our toolbox? That would be the hash table. It is the absolute sprinter of the data structure world, but as we're about to find out, it has a pretty major blind spot.
A hash table is just brilliant in its simplicity. You give it a word, let's say dog. A special hash function instantly converts that word into a unique address, pointing you directly to its location in the dictionary. There's no searching involved. It's a direct jump. This is what we call an O of 1 or constant time lookup. It's as fast as it gets, period. But here's the catch, and it's a big one. This slide reveals the hash table's fatal flaw. It is fantastic for an exact match like book, no problem. But for a wildcard query like book, it is completely and utterly lost. That hash function needs the entire word to calculate the address. There's no concept of alphabetical order or neighbors, so it has no way to find book, books, or booking. It's just impossible.
Okay, so the hash table is out for wildcards. We need something way more flexible. And this brings us to our first really clever solution, one that's designed specifically to handle those starts with queries, the trie. A trie, which is also called a prefix tree, organizes words letter by letter. I want you to imagine one of those old-school physical dictionaries with the nested tabs on the side of the page. First, you find the tab for C, then inside that section, a tab for A, then R, and so on. In a trie, each path from the very top of the tree down to a special end node spells out a complete word. So when we search for something like cat, the process is super intuitive. We just walk the tree. We start at the root, go down to the C node, then from there down to the A node. Once we're at the spot that represents the prefix ca, the query just becomes, hey, find every single word that can be formed from this point onward, and the tree's structure naturally leads us to all of its descendants, car, cart, cat. For prefix searches, our problem is solved. Now, tries are a huge improvement. They give us lightning-fast prefix searches, and they're still great for exact lookups too. But, you guessed it, they have drawbacks. For one, they can use a lot of memory. But more importantly, they only solve the prefix problem. What if your wildcard is in the middle, like Twitzen, or at the beginning, like Ontrischen? Yeah, the trie structure can't help us there at all. To solve for a wildcard anywhere in a word, we need a totally different, kind of mind-bendingly clever approach. So let me introduce you to the permuterm index. This right here is the genius idea at the heart of the whole thing. It basically says, what if we could take any wildcard query, I don't care how complex it is, and magically twist it around so that it becomes a simple prefix query, the kind of query that a structure like a trie could solve in its sleep. Okay, here's how it works. It sounds a little weird, but stick with me. First, we add a special symbol, usually a $sign, to mark the end of the word. Then, we generate every possible cyclic rotation of that string. So for helmet dollars, we get elmet dollars H, then lelmet dollars each, and so on, all the way around until we get back to the start. We store all of these crazy rotations in our dictionary, and every single one of them points back to the original word, helmet. So how does this craziness handle a query like heat? Well, first, we add the $sign. Then, here's the trick. We rotate the string until the asterisk is at the very end. So heat star dollar becomes et dollar heat. And now, look at that. We can just search for the prefix et dollar heat. Our index finds the rotation et dollar helm, which points us straight back to our original term, helmet. It's an absolutely brilliant transformation. Now, the permaterm index is incredibly powerful, but it comes at a steep price. The index size is massive. I mean, storing all those rotations for every single word takes up a ton of space. So in the real world, many systems use a more balanced, practical approach, the K-gram index. A K-gram is just a fancy way of saying a chunk of a word that's K letters long. Think of it like breaking a word down into a bunch of small overlapping Lego bricks. If K is 3, we're talking about trigrams. If it's 2, we call them bigrams.
So let's look at the word hello. First, we pad it with special characters to mark the beginning and end. Then we just slide a little window of length 3 across it. This gives us our 3 grams, or trigrams. $SH, then hell, L, low, and low dollar. Our dictionary now maps each of these tiny pieces to a list of all the words that contain them.
So how does this help us with a search like cat lay? Simple. We break the query itself into its own K-grams, $C and lay. We go to the index and ask, hey, what words contain $C? And we get back a list of candidates like cat, cattle, and cart. Then we ask, okay, what words contain lay? And get another list, which includes cattle. And here's the key step. We find the intersection, the words that appear on both lists. In this case, that's just cattle. We do a quick final check to confirm it actually matches the cat-lay pattern, and boom, we're done.
And get this, there's a really cool side effect to this whole K-gram structure. It's fantastic for spelling correction. If you accidentally type board, the system can look up its bigrams, bow, or, and ard, and find other words that share a lot of those same pieces. This quickly gives it a short list of likely candidates, like board, that it can suggest to you. Pretty neat, right?
So we've looked at 4 different approaches, and each one has its own set of strengths and weaknesses. In engineering, and especially when you're building a search engine, there's almost never a single best answer. It is always about picking the right tool by balancing the trade-offs.
This table really brings it all home. The hash table is cheap and super fast for exact matches, but it's completely inflexible. The try perfectly solves our prefix query problem, but costs more memory and can't handle any other kind of wildcard. The permuterm index is the superhero that can do it all, but at a ridiculously high space cost. And finally, the K-gram index kind of hits that practical sweet spot. It's pretty good at everything with a manageable memory footprint, which is why it's such a popular choice in a lot of real-world systems.
It's this fascinating puzzle of efficiency versus power. Is the system you're using optimized for pure raw speed or for maximum query flexibility? Or maybe it's all about saving as much space as possible. Now you know the secrets happening behind that blinking cursor, and you can really appreciate the complex, clever engineering that makes a simple search feel just like magic.